All right, let's get started. So hello, everybody. Welcome back to Comp 2160. It's nice to see all of you. It's nice to see all of you. It is nice to see all of you. I hope that you're all doing okay. We are getting real close to the end of this course. We are getting real close to the end of this course. And I'm probably going to say this every single class now. We're getting really close to the end of this course, and I'm looking forward to the end of this course. I do like seeing all of you all the time, but I'm also looking forward to riding my bike in the sunshine and having a little bit of time to do other stuff. So today we're going to be doing some sample stuff using the sample solution for assignment 2, and I'm going to be doing these things on Aviary. I'm not planning to edit this code in any way. I just want to use this as an application to do some performance testing and profiling. So if you want to follow along with me, please make sure that you've got that on Aviary already. Today, what I am hoping for you to be able to do is to describe the benefits of modularity and use simple metrics to specify the degree of independence, such as coupling and cohesion. So as with last time, coupling and cohesion are two keywords that we're going to be using to make measurements about software. So we're going to be using these words to try and describe the relationship between two pieces of code or two fragments of code that we've got. The other thing that I'm looking for us to start doing today is, given an existing solution, identify and explain where the use of appropriate data structures, algorithms, and/or techniques such as caching and lookup tables provide better paths to optimization than low-level code. We think way back to the beginning of this course, which was only 5 weeks ago. One of the questions that I asked you was, why would we want to use C in a course like this? And I remember that lots of people were saying things like, well, C is high performance code. This is code that's going to be fast. It can be, sure, it can be, but what we're going to be thinking about here is less about using low-level code, so less about using C, less about like taking something and then implementing it in assembly language programming, and a lot more about how do I make design decisions about the software that I'm building to try and make sure that it works efficiently, but it still works the same way that it did before. The way that we're going to be starting this today is to try and identify where the problems are in terms of performance. So we're going to be using tools to help us try and identify where the slow parts of our code are, and then to inform us about what parts are slow, so we can then look at those parts to try and say, these are the parts where maybe the choice of data structure that we've got here is not the right data structure for what we're trying to accomplish. So, in terms of the first learning outcome, we're going to be looking at this from the perspective of modular design. These buildings right here, these are in Montreal. I don't know if any of you have been to Montreal in the last 50 years, but these were built in 1967. There was like a World's Fair in Montreal, and this is called Habitat 67. And these are just apartment buildings now, and people just live in them, and they're just like these cubes that are kind of randomly stacked on top of each other. And somehow that's related to modular design. So the goal that we have for modular design is that we want to separate our code into reusable objects, reusable code objects, or reusable code like fragments or things. There's two approaches or two things that we're going to do with this. We're going to try and identify logical subsets of code that will help us get to that, and then abstract data types and data structures. So when we're thinking about modules and modular design, we're thinking about trying to get things that are all kind of related to each other, logical subsets. Abstract data types, we've started to do this in this course using the stack data type. And then data structures. We've started to do this in this course using the list data structure to implement a stack. If you've got an idea for something that you want to build, as you're designing it, one of the things that we want to start thinking about Or alternatively, if you've got a solution to something and you want to start trying to modularize it, so take the code that you've got and then take it and break it down into smaller pieces, we have to start thinking about how we're going to accomplish separating this code, this big piece of code, into different smaller parts. In terms of thinking about ways to separate code, one good thing to immediately think about is how many lines of code are in a function as a measurement of how much time should I be spending to separate something. This is a good starting point, but it's not really necessarily a good way to organize the code. This is something that says, yes, maybe this should be separated into smaller parts, but lines of code in a function is not necessarily a good measurement of, I need to actually separate this, or how do I go about accomplishing separating this into multiple parts? Similarly, lines of code in a file, while lines of code in a file is a good measurement to say that there's lots of functionality in something, that doesn't necessarily help us decide where to make those breaks, where to separate these ideas into smaller parts. I want us to think about a specific software design principle that's called the single responsibility principle. So this is part of a set of 5 design principles that are called the solid design principles. You will learn a little bit more about the solid design principles in Comp 2150, which is object orientation. You will learn a lot more about each of these software design principles in Comp 3350 in software engineering. We're going to think specifically about the single responsibility principle when we're thinking about separating pieces of code into smaller parts. The single responsibility principle is pretty straightforward. It's do one thing and do that one thing well. The code that you are putting into a module should have one single responsibility. Let me take a thought about the way that we've designed assignment 2, for example. With our stack implementation, we have a stack implementation. It doesn't print anything out. The stack itself doesn't do bracket matching. The stack itself is doing one thing, which is be a stack of integers. That's all this thing does. There's 2 main targets. We want to identify reusable abstract data types. So these are things like stacks, queues, sets. These are the abstract data types that we're thinking about here. And then the data structures that we are using to implement those abstract data types. So things like lists or hash tables. Have you done hash tables yet in 2140? Yes. If you're taking 2140 right now, you've done hash tables? Yes? Okay, good. So hash tables is another data structure that we could be using to implement things like a set, for example. We want to separate code into these reusable abstract data types and reusable data structures. We also want to look for design patterns. Again, design patterns, this specific keyword, you are welcome to click on this link, but it's out of scope for this course. Design patterns is something that you will see in Comp 3350 software engineering. And design patterns are kind of like, these are common structures for solutions to problems that people have. So one example that I can come up with is when you've got an Android app, a lot of Android apps will want to send messages to the person that's holding the phone, like pop-ups. And there's a pattern, a design pattern that can be used here to say that I want to, at the Android level, I want to watch for messages from this specific thing. So I'm going to subscribe to messages from this specific thing. The apps themselves will publish messages to this queue of messages that are being used by the Android application or the Android operating system itself. These design patterns aren't like you can just download a piece of code and then just dump it into your code, but it's going to be structured the same way for different implementations. So subsystems and design patterns, and we'll talk specifically about what subsystems might mean in just a couple of seconds. The kinds of abstract data types and structures that we're thinking about here in this course are things like lists, sets, and trees. And if you're implementing something that has a list, a set, or a tree, then each of those is going to get a .c and a .h file. In terms of C, in terms of what we know right now, we're going to have to build an integer list. We're going to have to build a character set. We're going to have to build a string tree. We're going to have to build a string tree. We're going to have to build each of these things separately, but each of those things is going to get a .c and a .h file. Subsystems are collections of related functionality that don't fit into this big header of abstract data types and data structures. So collections of related functionality to me are like the standard IO library. stdio.h, standard IO, contains lots and lots of functionality related to input and output in a C program. So this is where all of those functions like getChar and putChar, fgetS, scanf, printf. This is where all of those functions live in the standard C library. This is a subsystem for the standard C library. When we're doing this in Java, we're grouping these things together as modules. And the word module here refers to classes in Java or a package of classes in Java. Did you do packages in 1020? No? Okay, so packages is kind of like a file folder structure for related classes. So when you have the java.util.list class, the util is a package of related things and data structures that you might have in Java. You will see package more in Comp 2150 in programming object orientation. In C, this is going to look like literally folders on our system. We're going to make files and folders that represent different groupings of related functionality, and we'll have headers that represent all of that related functionality. These modules, these subsystems, may use the ADTs and data structures that you're building up in your other parts of your system. They're not mutually exclusive from each other. And each of these subsystems either gets a folder or a .c and a .h file. Still, how do you go through the process of defining a subsystem? So what kinds of things actually go into a module or a class? What kinds of things go into specific functions? And then what we're going to think about here in terms of defining subsystems is how do modules and functions relate to one another in these subsystems? We're going to be looking at this from the perspective of I want to make measurements about existing code, so modules and functions. And based upon the measurements that I make with those existing code, I'm going to try to make decisions about how do I take these things and separate them apart. So there's two concepts that you can use to measure subsystems in general. This is not a C-specific thing. This is just programming in general. There's cohesion and there's coupling. These are the two words that we are going to use to make measurements about subsystems. Cohesion is a measurement of how well pieces of code and concepts belong together within a single unit. So whether it be a function, a whole file, a whole .c file, or an entire grouping of related things, how well do these things all belong together? stdio.h is a cohesive piece of code because all of the functions that are declared in that header file all have to do with input and output. We could further separate it and say, I want to have stdi and stdo separately, but it's okay for these things to belong together. These are cohesive. Similar thing, the idea here is that similar things should be close together. Again, single responsibility principle. Do one thing and do it well. The one thing here for cohesion and grouping things together like stdio is do input and output well and do it. That's the one thing that we're doing. When we're thinking about code, we're going to have this idea that classes and modules are implementing one concept. So just one action or one abstract data type or one data structure. When we measure cohesion, we're measuring it kind of like hand wavy and kind of vague. we're only going to be using high and low. We're not saying things like this is 70% cohesive. We're not saying it's 50 cohesive. We're saying it's just high cohesion or low cohesion. There's not going to be much in the way of specific numbers here. The other word that we're going to use to measure software design and modules is coupling. Coupling is the measurement of how much one unit of code, one thing, depends on the specific implementation of another unit of code or thing. If we have really high coupling between two pieces of code, so I've got one unit here that depends on the specific implementation details of another unit over here, it makes it very difficult to change the other unit that is being depended on. It's difficult to change the implementation of details of that because this other unit relies on that specific implementation. Changes that we're making to one thing are affecting other things in this overall system that we've got. As an entire concept, coupling is unavoidable. So it's not a good thing to have high coupling, but we can't make coupling zero. If we made coupling zero, we would have things that never interacted with each other and never used each other. We don't want that. We want to be able to build on software. Some coupling is unavoidable, but we can use this idea of designing modules to help control or reduce the coupling. When we're measuring coupling, we're using two words generally to describe it. It's the same general idea as cohesion, like we're going to be one or the other, high or low, but you might also hear people using the word tight or loose coupling. This is tightly coupled to one thing, or it's very loosely coupled with another thing. Yeah. 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 So in terms of subsystem and preprocessor versus implementation versus library, when I'm thinking of subsystem, I really actually just want to use the word library. I don't want to use the word preprocessor. Excuse me, I don't want to use the word header. I don't want to use the word C. I don't want to use the word Java. I really just want to say this is a library. So the standard IO library in C is an example of that. We've only interacted with the standard IO library in C in terms of including that .h file. That's how we get access to those functions. That's how when we compile our code, we're able to link to those functions ultimately. But that's a specific implementation of this idea of subsystems. In Java, there's the system.out property. There's the system class, which itself is a subsystem. There's output streams in Java, which is their own kind of independent subsystem or data type. And they accomplish the same thing as what stdio.h is doing in C, but it's kind of this separate thing. So when I'm thinking about coupling, cohesion, modular design in general, I'm not specifically thinking about C or preprocessors or anything. I'm really thinking very vaguely and kind of generally about the idea of a library. Yeah, does that answer your question? Okay, okay. So I'm gonna go back to here. Coupling is measured as high or tight, so tightly coupled or high coupling. It can be measured as loosely coupled or low coupling. Are there any other questions about this before I move on? Because I'm gonna rant about something for a second. Okay, so my rant is about modern phones. It used to be about just iPhones because they were the first ones to do this, but now it's about phones in general. And my rant is specifically that in my mind, there's something missing here. There's something really important that's missing here. You know, I don't know how often you smash the screen on your phone. It seems to be getting better than it has been in the past in terms of the hardness of screens and the durability of screens. Whether you put a screen protector on or not or whatever, it seems to be getting better than it was. But it used to be that you like look at a phone the wrong way and the screen would just crack. And then it's kind of like, I just have to go buy another phone. And when this was starting to happen, I was very much in that state of my screen has just cracked. And I had actually just ranted to a class previously about how can people walk around with cracked screens? Like, how does that even happen? And then I go to class the next day with this cracked screen on my phone because it fell out of my pocket when I was sitting in a lawn chair. And so I started looking at phones, and I saw that it was getting to be difficult to buy a phone with something that I could plug this into. Now, I don't really use Beats. I don't know or care what people who consider themselves to be audiophiles think about Beats or other headphones, but I just have headphones that I like. I like being able to plug my headphones into a device and then know that they will work. In terms of coupling, headphones have this 1/8-inch jack on the bottom of the wire, and you can plug it into something that has an 1/8-inch port that will accept that jack, that plug. And it doesn't matter what it is. If I've got my headphones, I can plug them into my laptop. I could plug them into the desktop PC that's down here. I can plug them into the bottom of my Game Boy so that my parents don't have to hear this terrible music playing for hours at a time. It doesn't matter what it is. My headphones in this state are very loosely coupled with this idea of plugging things into an input port or an output port. But phones now, despite me maybe spending a couple $100s on these headphones, don't have something that I can plug that into. There's something missing here. And so, I mean, a solution is to just make your own. But that obviously just gets us back into the first problem of having a broken screen. And that leads us to the next logical step. And I'm going to point specifically at Apple now, where they made headphones that were like this. These are what used to be around before they had AirPods. And you could buy these headphones that would have a lightning connector on the bottom of them. And you could use that very specifically with your iPhone. Like, I can't plug that into this because it's a USB-C port. I cannot plug that into my laptop because I do not have lightning ports that Apple has. I cannot plug it into the bottom of my Game Boy because my Game Boy was 20 years old when the lightning port came out. I would have to go and buy these headphones for $100 and then only be able to use them with my iPhone or my Mac. These are very tightly or high coupling with Apple's ecosystem. Yes, I could go out and buy something like this. And I have, in fact, bought something like this. But I kind of have to go and like spend money to do that. And I don't really want to do that because I'm cheap and I'm curmudgeonly. Let's do a quiz. So this is a quiz that consists of 4 quiz questions, and then there are survey questions after that.
giant bones were actually such a nightmare to fix. They specifically designed them so that like there were like flat tables that like you could break the bone, and they were like over top of right underneath things that you probably need to replace.
Okay.
Specifically because if you broke from a cell mechanic, the company would have to buy a whole new iPhone. And they did that on purpose. It's literally like they made them hard to replace without breaking, so that you would break them.
We might imagine that Apple is getting better and that you can like rent a whole repair case from them, but they actually ship this giant Pelican case to you, and it's got all these jigs that you need to like remove the glass and stuff. Yeah, it's kind of dumb.
But they want you to buy that from them.
Yes, of course you have to rent it from them. Yeah. That's it. This is a topic for a completely different class. If you want to talk about things like the ethical behavior of companies like Apple and John Deere, which is something you probably wouldn't imagine, but John Deere specifically, yes. If you want to think about those things, take Comp 4620, which is Professional Practice of Computer Science. I'm standing here all the time just pitching all these other courses to you. Okay, so let's get going. Remember, there's 4 quiz questions, and then we're going to have some survey questions. Okay, good. I'm really happy that nobody picked the one here in the middle. This absolutely is what I would consider the major goal of this idea of modular design. We, again, have been spending, I want to spend more time thinking about how to measure how interrelated things are and how intra-related something is. But ultimately, our goal with these measurements is to identify the things that we can take out and then reuse them again later. Hiding implementation details and separating our interface from implementation are positive side effects of doing that. I want to take something out, and I want to make an interface from it, and I want to use that interface. I want to make sure that I'm able to depend on the interface's specification as opposed to how it's been implemented, and I want to be able to hide implementation details. But the major goal here is make code and concepts easier to reuse. Here's our next question. Good. Okay. So does this complete structure definition? So I'm thinking specifically about the word struct and then like all the properties and then the semicolon at the end. No, that information is private. When you get to operating systems, so again, Comp 3430, when you get there, you're going to see that there's a bunch of stuff in the Linux kernel that exposes the structure. You have to know what the structure is because you're asking the kernel and the operating system to give you specific information. But generally, when we're doing modular design, no, that information is private. I don't want you to know what's inside my object because I don't want you to depend on the implementation details of my object because I want to change my object whenever I want without you having to change your code. How will the clients know what's inside my object? That's a fair thing to say. It is a fair thing to say. The way that we're going to tell clients about what's inside my object is by making an interface for them that allows them to ask questions about what's inside my object. But I don't want you to know what the actual structure is that I'm using internally. In my string example, I don't want you to know that I'm using an array or a list. I want you to get characters out of my thing, but I don't want you to know how I'm actually doing it internally. Yes, otherwise I get compile errors about unknown types and sizes. That's fair, I guess, but there are ways around that. And no, the client code should declare this. I suppose that's possible, but I'm glad nobody picked that, so good. Yeah, it should be declare. I'm just bad at spelling. Here's the next question. Oh, I'm terrible at spelling. All right. How much must a client know, or how much should a client know about the implementation of an interface? Nothing. It really shouldn't know anything about the implementation of an interface. A little bit, sometimes it happens. Sometimes it happens. Again, what I've just said. In the Linux kernel, sometimes you're going to make calls and requests to the operating system. Please tell me about this. The thing that I can think specifically about is the time. What is the time right now? And you have to pass a structure where you know what the properties of that structure are. Sometimes a little bit more is kind of a joke answer. And so I hope that that one person realizes that's a joke, and a client must know everything about an implementation to use it. It doesn't have to know anything about an implementation to use it, as long as it knows what the interface is. Mega evolved Pikachu. Okay, all right. Wormy guy and dad is the fastest. Very nice. Okay, here's the last quiz question. We're going to keep doing questions after this, but they are survey questions after this. Okay, good. You know, this is definitely true. My mom and dad don't care about how I implement my interface, because my mom and dad are going to say really nice things about whatever code I show them, because they're my mom and my dad. I don't need to care about how I implement my own interface. We do have to care a little bit about how we implement our own interface. So you can change the implementation without affecting our clients. And we've seen that. So with our strings, we were able to recompile that main code without changing the main code. We were able to recompile it with both implementations without making any changes to it. Okay, so great. This is the end of our leaderboard. There's the turtle on there. And Meow is on top. Congratulations to Meow, whoever Meow happens to be. Okay, so what follows now are some survey questions. They are specifically about coupling and cohesion. I'm going to show you some pictures. I'm not showing you code right now. I am going to show you code at a later time with relation to these specific topics, but right now I'm just showing you pictures. They are abstract ideas. And what I'm looking for you to do with these abstract ideas is measure coupling and cohesion within the abstract idea that we're looking at here. So let's take a look at the first one. We've got a big box of Lego on the side here. And what I'd like you to do is measure coupling and cohesion for this image. Whoops. I'll give you about 10 more seconds to answer, and then I'll start talking about it. Okay. All right. So what I think about this, you are welcome to your own thoughts here, but what I think about this is that this is a highly cohesive picture. This is a bin that is filled with Lego, and this bin of Lego looks like they are all pretty much the same part. They're all a little bit different, but they are all pretty much the same part. They're the like rectangular pieces that are common when you're building structures. Like I want to build a house or I want to build a plane. Plane is a bad example. I want to build a house. That's it. I want to build a house. I want to build a fence. Yes, okay. I think that this image is a highly cohesive image. It contains entirely Lego, and of all the Lego pieces that are in it, they all look approximately the same. I wanted to make a little bit of a joke about how these are tightly coupled, because when you press them together, sometimes they are impossible to take apart. But I'm going to say that this is a loosely coupled thing. One, they are loosely distributed in this thing. They are not connected to each other. However, if we take a Lego piece here and we take this Lego piece here, we can put those things together. There is some coupling, and I mean this in the abstract sense. Yes, the literal sense, but also the abstract sense here. There is some coupling between these things, but if you have Duplo, so Duplo is like the little kid version of Lego, and they're bigger pieces. They are made by the Lego company, but they are little pieces. Big pieces. They are big pieces. They are bigger pieces. They are made by the Lego company, but they are bigger pieces. The spacing that's in here will fit correctly onto Duplo pieces. Duplo pieces will fit correctly onto the spacing of these pips. They will fit correctly onto there. So this is loosely coupled in that this specific thing is not necessarily dependent upon in terms of the way that it's implemented. These are all made of plastic. I can make these bricks out of other materials, and as long as they satisfy that shape, the interface between these things, I can put them together. So I think that this is a fairly loosely coupled and highly cohesive image. That's what I think. And it looks like we're all mostly on the same page as me. So I'm good. I'm happy to see that. Any questions about this? Okay. Here's another one. I'll give you 5 more seconds. All right. This is a bin of Lego. And this bin of Lego, unlike the last picture, has like lots of different shapes of pieces. I still believe that this is loosely coupled, even though we have pieces of Lego here that depend on, I forget what the name of the Lego is that's mostly just like where you got rods and stuff. Is there a different name for that? Technic, yeah, thank you. So there are pieces in here that depend on those rods being present, like in Technic, but again, it's kind of a Lego thing. And if you get literally just have a, I don't know, a stick of some kind, you can just shove it in there and use it for the same purpose. In terms of cohesion, I would agree here that this is less cohesive than the last picture we saw. The pieces are going to be different kinds of things. It's less cohesive. But I'm going to say that I personally think that this is still in the middle here in terms of cohesion. And the reason that I'm saying this, and I'm going to tie this to code, is we have a library that we've been using called stdio.h. And stdio.h has both input and output in it. And while those two things are definitely related to each other, they are different. One of them prints stuff out, and one of them reads stuff into memory. In this picture, I'm going to say that this is kind of in the middle of cohesion, and I think we're both me and you as a group are saying approximately the same thing. That's okay? Okay. This is a webcam. You can it's literally the same model as what you see on here, and it's a USB webcam. All right. I love that this is in the middle right now. It's just all over the place. I'll give you 5 more seconds. Yes, we've got someone in each corner. We have many people in each of the corners that we have on this thing. So first and foremost, I'm showing you pictures right now. We're talking about software concepts so that everyone may independently be interpreting this image differently. That's totally fair. I'm going to tell you what my several interpretations of this image are. In terms of, this is a USB webcam. So USB, just in case you've all forgotten, looks kind of like this, like that. It looks like this. And you can jam this into a USB port in the side of a laptop. I believe that in terms of coupling, the webcam itself has fairly loose coupling. This connection itself has fairly loose coupling. I can plug this into my laptop, and as long as you have a USB-A port on your laptop, I can plug it into your laptop. From a perspective of, and this is stuff that's like outside of maybe your domain area, and that's, again, it's totally fair. From a perspective of what this webcam implements a protocol, an agreed upon protocol for when I'm connected to a computer, I'm going to present myself as a generic video device. The operating system that I've got here, so I'm running Linux. If you plug this into a Windows machine and you open the camera app, generally it's just going to work. If you plug this into a Mac and you open up Zoom, generally it's just going to work. Because webcams have this protocol that they implement that is generic video device. You can install special drivers, and special drivers are software that you would get with the webcam. And there might be special features on here. I don't know if there's any special features on this one, but you might have things like lighting that's attached to this thing that you can change the color of, but you can only do it if you install the special app that came with this thing. If we're thinking about it that way, we've got a special app that's necessary to do it, then that special app is tightly coupled with that specific implementation of the camera because that's the only one that it's going to work with. In terms of cohesion, I think that this webcam device itself, it has a microphone and it has a camera sensor. I believe that it is highly cohesive. These are two different things, yes, but they are required for being a webcam, being a single unit that's capable of getting you connected to Zoom or Teams or whatever if you need to talk to somebody. So I believe that as this picture is, in my mind, it's a loosely coupled, highly cohesive thing. In my mind, this is a loosely coupled, highly cohesive thing. If you have a different opinion about this picture, that's okay. But what I'm looking for you to be able to do with this is to be able to justify your decision. Why do you think this is a loosely coupled thing? Why do you think that it is a low cohesion thing? What is it about it that you've identified? And why do you think that that's the specific property or measurement? Any questions about this one? We're okay with this? Okay. There were so many that were just right up in the corner there right away. Put one in the bottom, in the opposite side. Okay, everyone is glomming onto that top corner. Is this what? It does kind of look like an arrow, yeah. It's looking like a stick figure, actually. Like, that's the head up in the top corner, and it's got arms that are going like this, yeah. And then two really skinny legs that are close to each other. Okay, I think that this is highly cohesive. You know, we've got a train and tracks. I'm thinking about these things together. These are highly cohesive. It's about moving stuff around. That's the thing that we're doing, is moving stuff around, and these are highly cohesive. I am actually going to say that I would move this down here. This is indeed tightly coupled with trains, yes. It's indeed tightly coupled with trains, but it is loosely coupled in general with trains. You can put different trains on the same track. It doesn't have to be this steam locomotive. It can be whatever train. It can be a diesel engine train. There's at least 5 kinds of trains. I'm sure there's at least 5 kinds of trains. But you can also put trucks on these tracks, because there's those trucks that have those tiny little things that push down and let them drive on train tracks. So in that sense, I would say that this is highly cohesive, yes, but it's more toward this loose coupling. It's very tightly coupled with trains in general, yes, but in general. I can put other trains on this thing, other implementations of a train, and it will still just run on that track. My understanding is that you cannot take a North American train engine and send it to Europe and have it go on those tracks. I think they're different standards, but within North America anyway, you can have just different kinds of trains going on the same track. Is that okay? Okay, here's the last one. Okay, I'll give you 5 more seconds. Okay, yes, I 100% agree with this. I think that this key and lock is very tightly coupled. You can use this specific key to unlock the lock. You cannot put other keys in here. You could try, but they're going to get stuck. I'll let you give a retort in just a second. You can use this specific key in this lock to unlock it. This lock's specific, barrel, whatever this thing is called, is very tightly coupled with the actual key that's designed to fit in there. I think that this is also highly cohesive. These two things belong together. They are both together used to prevent someone from getting in. Yes, what is your point? Please make it. What about cutting keys or picking locks? So sure, I guess if we want to go beyond this picture, I could take this to Walmart and stuff it in that machine and get a copy made of that key. Or you can hire the lock-picking lawyer and have him come to your house and open up the lock for you, I guess. But in this picture, I'm thinking about the lock and the key that are in the picture themselves. Yeah. So I'm really happy that you brought that up, but I'm also really happy to see that everyone's picking pretty much the same thing I am here. Yeah.
So let's say something I want you to put on record.
Okay. Yeah. Well, okay, so if we're going to go to locksmiths, then a locksmith can come and take that barrel out and put a new one in for you. Yes. It's still cohesive, yes. Yeah. I think that the argument here is that if you include locksmiths and lockpicking, then it becomes less tightly coupled because you can get around that thing. Yeah. I still stand by my point, though. I think that this is a tightly coupled and highly cohesive image. Okay. All right. Thank you for that. So what I would like to do now is, like I said, these are abstract ideas and abstract concepts that we're using to think about these two measurements of software. I will show you actual software to make measurements about later. But what I'd like to do right now is just spend some time taking a look at my approach to the sample solution for assignment 2. So I'm going to pop open on Aviary, the sample solution that I posted to the course webpage. And the approach that I want to take to this is I would like to take a look first at my implementation of the stack, and then look at my testing of the stack, and then look at my 2 bracket matching implementations. So I'm going to open up the stack first. And stack.c here uses a linked list structure to implement the stack. So I've got a node and I've got a stack data type. The node data type is private to my implementation. So this is not something that's exposed in the interface. I can't use it anywhere. But we weren't allowed to make changes to the stack's interface. So we couldn't put that node structure into the interface if we wanted to. This is a linked structure, so my nodes all have a pointer to next, and these are a stack that's going to include integers only. The only thing that I'm going to want to put into this stack is integers. I have uninvariant for my stack here, and the invariant for my stack, which is implemented as I have a top or a head to my stack, and then I have a count of the number of elements that are in the stack. My invariant here is that the stack itself must not be null, and the head of the list can only be null if the number of elements is 0. So if I don't have any elements in my list, then I should have no nodes in my list. I've also got something here that's going through and counting up all of the nodes in the list to confirm that the nodes that I'm able to count before I get to the end of the list is equal to the number of elements that I've got. When I started implementing this code, my main point of starting was on these 2 structures and writing those comments. So I didn't write any functions or anything until after I had written out the structure that I want to use and then the comments. The comments here are the invariants of what I want to have for each of these 2 structures that I've got here. And I'm trying to make sure that after I've written those things out, that I'm going through and actually enforcing those invariants in the invariant function that I've got. After that, I'm going through and I'm basically just implementing the interface. So to create a new stack here, I'm using dynamic memory allocation, and then I'm checking to see if the value that I get back from malloc is null or not null. And then before I return this, one of my post conditions here is that I'm returning a valid stack to the caller. When I'm destroying the stack, I am expecting there to be a valid stack that I'm getting as input, and then I'm going through and releasing each of the nodes one by one. As I was looking through some of the submissions, some people also used pop to do this. So instead of rewriting this code to destroy the stack and walk the whole list, you just call pop repeatedly, which is also a perfectly valid solution. It's a little bit more elegant, actually, than I think mine, because you're just reusing the pop function as opposed to adding something new that steps through the stack. The push function here is going to go through the process of allocating a new node and then verifying that we've got a valid stack at the end. The peek function is fairly straightforward. I'm not making any changes to the stack implementation or the stack structure itself. So I'm doing a validation and then checking to see that they're still met with conditional statements, but I'm just returning the top value from the stack. Pop is removing one element from the stack. And then size and empty at the bottom here are just using properties of the stack that I've got, but assuming that there's some valid input for the stack structure. that was a very quick step through. Does anyone have any questions about the structure of the stack implementation? I think it's okay. Okay. So then what I want to do is I want to take a look at the test suite, the test harness that I wrote. Yours doesn't have to look like this. It doesn't have to look exactly like this. It's going to be like how you are approaching structuring the code. One thing that I did see as I was going through some of the submissions was that some people were using assertions in their tests. We didn't use assertions in our tests for the code that we were writing in class, and I wouldn't advocate using assertions in your tests just in general, because we want to be testing with and without the debug options set when we're compiling our code. So when you're writing test harnesses, you should be using just conditional statements to get the values for, to test the values that you're getting back from a function. You didn't have to be fancy and have red and green color codes here. I just wanted to stick with the same kind of structure that we had for the initial bracket matching test suites that I gave to you for the first assignment. The structure of this code is that I'm kind of going through and doing a bunch of different exercises with what I've got. So in this function, I'm creating a new stack. I'm trying to do a bunch of stuff with an empty stack here. And these are most of the edge cases that I've got. When I peek at an empty stack, I should get false back from that function. I shouldn't be able to peek at an empty stack because there's nothing on the empty stack yet. I shouldn't be able to pop from an empty stack because there's nothing on the stack yet. This function should return false to me. The size of an empty stack should be 0, and an empty stack should be empty. I should be able to destroy an empty stack at the end, and then the else part here is I couldn't create the stack in the first place. This function here is pretty much my entire edge case suite for my stack implementation. You might have had individual functions for each of these. So like create a new stack, test to see if it's empty, destroy the stack. Create a new stack, try to peek at it, destroy the stack. Create a new stack, try to pop from that stack, destroy the stack. That would also be okay. That would also be completely okay for this. I've got a function here that separately is just test to see if I can create a stack. So independent from the edge cases, I'm just trying to see, can I create a stack and then destroy the stack that I have created? I've got a function here that calls just push and then just peek. So I'm never trying to pop anything off the stack. I'm just pushing a bunch of stuff onto it and then trying to peek a bunch of stuff off of it. So push one time and then peek to see if I get the thing back that I was expecting to get back. After I push and peek, what I'm trying to see is I want to make sure that the contract of peek doesn't change the stack has not been violated. So I want to make sure that my stack size is still 1, that the stack is not empty, and then at the end I'm destroying the stack. In this test case, I'm going through the process of creating a stack and then just pushing a bunch of stuff onto it. And then afterwards, what I'm doing is testing to see if I can peek at it, and then also going through the process of once I've pushed that stuff on, I want to make sure that when I pop everything off the stack, that it's in like the reverse order of what I pushed it on. So the last thing that I pushed onto the stack should be the first thing that I pop off of the stack in this test case. And then after I've popped everything off the stack should be empty. And then I've got my main function here at the bottom. Is that okay with everyone? Any questions? Yeah.
I thought I heard at one point that we didn't have to test to destroy the stack.
So I'm not really testing destroying the stack here. I'm calling destroy stack to destroy my stack. I can't know what my code from this side of the interface, I cannot know what my code is doing internally with the stack that I pass to it. I'm just trying to make sure that when I create something, I release the resources that I've acquired. If I don't have destroy stack in this, the functionality is still going to be the same. So in that sense, you can't really test destroying the stack. I just want to be able to pass it a stack and just see that it returns. That's all I'm doing here. So I can't go in and say like, are the insides of the stack null now, because I don't have access to the insides of the stack.
But you still did like if make sure.
Well, because destroy stack returns a Boolean value, so I just want to test to see that it returns true. That's all I'm doing with that. Any other questions? Yeah.
Which test case was the true one?
Which of the stacks that I gave to you? So I put that in the README. If you take a look at the README for this, but I will go through and I'll let you know. The stack 1 implementation is that the empty function always returns true. So no matter whether there's any nodes in the list or any elements in the stack, it's just always returning true. The second stack implementation is the correct one. That's the one where there's nothing wrong with it. Great job, Franklin. I wrote that to myself. Great job. Stack 3 is implemented using an array instead of a list. So once you push past 10 items, you can't push anymore. You just keep pushing, and then eventually you're just going to get the 10th item that you pushed onto it. Stack 4, the pop function is broken. And this is kind of simulating like what happens if I get next instead of, if I get next instead of next to like pull something out of the stack. So if I do head is equal to next instead of just next, I'm popping 2 things off. And then stack 5, the peek operation violates the contract. So it's actually popping things off as opposed to just peeking and not changing the contents of the stack. Yeah.
What I found out was that
The top is always 0? Okay. I mean, as long as you can show me that your tests reveal that behavior, then that would be reasonable to have. Yeah.
on that stack 3, whenever it pushes, it makes the new node point to the head node, and it makes the head node point to the head node. So that the head node always stays on top after you push.
Okay. That might also be a way that it's broken. Specifically, though, I tried to just do this with a limit of 10 elements. Yeah, this one was tricky because it's kind of like, yeah, it's going to be breaking from multiple perspectives. So as long as you have something that reasonably says there's something wrong with this and what's describing what's wrong with it, then the grader should be giving you credit for it. Yeah. I mean, without reading your answer, I don't know that I'd be able to tell you for sure. But I mean, as always, if you have questions about what the graders have given you as an assessment, please feel free to contact me afterwards. I was just able to get this out to the graders fairly recently because it was just due fairly recently, but you should expect to get feedback from them next week. All right. So the other thing that I wanted to take a look at was my, my bracket matching. So I did this in 2 ways in terms of the input that I'm getting. So the input approach here was that we're kind of expecting, we don't have a statement of how long the lines can be anymore. So I've got 2 functions in each of these that's called find match and print match. Find match is the one where I'm given a position that I'm trying to find the matching bracket for, and it returns the matching position or -1 if it's if there is no match. And then the print match function just takes both of those open and close, or it takes -1 to say that there's no match and just prints out the X's. The main function here is where I'm doing the input stuff. In this one, in match.c, I'm doing input 1 character at a time. So I'm constantly getting 1 single character, and then I'm doing realloc to change the size of it by 2. So in terms of, I want to have a 1 character string up here at the top, A one character string is two elements in an array of characters where we've got just the first character and then the null byte. And then I'm going to keep reading until I get this new line character and keep resizing the line by plus two elements, basically. I want to keep adding one more character plus another null byte to the end of this thing. Once I've got a full line of input, so this goes up until we read that new line character, then I'm going to use this stir function to find the last instance of a space character, and then I'm using a2i to pass that to a target, like a location that I'm trying to find, and then I'm calling both of these functions here that I've implemented to do the bracket matching part. The find match function is implementing the algorithm that I described in the assignment document. So the find match function is down here, and it's just using the stack to push and pop things off as we're finding brackets, opening and closing brackets in the string that we're reading. And then the print function is it's a print function. It goes through the process of printing out characters one at a time. I'm going to go back up here, but are there any questions about this approach? Okay, and then the other thing that I did was I put a solution for the bonus up, and this one uses a different approach for doing input for arbitrary sized lines. This one uses fgetS instead of getChar, and the idea here is that it's kind of the same structure. I'm going to get a line of input from standard input. I'm going to get up to a certain number of characters from standard input, and I'm just going to keep getting characters from standard input as a line until the last character in the line that I've read is the new line character. That tells me that I've read the end of a line. For each of these, I'm calling fgetS, and then I'm using this realloc, and then I'm using a function from the string library called strncat that says add this to the end of the string that we've got right now. So I resize it, and then I add to the end of this thing. Once I've got that, then the matching part is pretty much the same. I don't call that find match function in here because I've mixed together the printing and the finding into one function. And I'm going to go down here, and the approach that I used for printing out colors is starting up here on set number on lines 69 through 71. The ANSI color codes, these are the ones that we were using to print out red and green. There's a lot of different ANSI colors that you can use, but there's about 17 that are printable on the terminals that we have access to. They all start at 30, so 30 is like the first one, and then it goes up to 47. And then we can kind of cycle between those using the mod operator. So on line 71 here, I've done this define to color, but I could have done this as a function instead of using the preprocessor directive to do it. But you can kind of just imagine that this is a function. And I'm using, as input, I get a number. I'm doing modulus on the range of colors. So there's 17 total colors, and then I'm adding the base to it. So this is going to go through 30, 31, 32, 33, 34, all the way up to 47, and then back to 30 again. As I'm going through the string, what I'm doing is, if I encounter an opening bracket, I push the current color to my stack. So I'm not pushing the location of this bracket, but I'm just pushing the color that I'm about to use. I print the bracket out. So this kind of messy looking string here is, this is the beginning of that color code thing. So \x1b and then opening square bracket. %d here is the printf %d code. I'm printing a number here. And the number that I'm printing out is to color the current color. And then I increment current color. And then this part is resetting it. Current color just keeps getting bigger and bigger and bigger and bigger. But when I call this to color thing, it's always going to be within the range of 30 to 47. And it'll just keep getting bigger and bigger and bigger. But I push that color onto my stack. And then when I encounter a closing bracket, I pop a color off of the stack. And if I have popped something off of the stack, then I print that color. And if we go through this process of push, 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 pop, 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 we're going to get the brackets that match each other having the same colors because we're pushing and popping those colors on and off the stack. If it's not a bracket at all, then I just print that thing out and I don't do any color modifications to it. And then I destroy the stack at the end of the function. All right. This is the bonus part. So, no worries if you didn't get to this point, but this is how I approached solving that problem, is just to use my stack and then use the color codes. Because they are numbers, just use the stack that I've got and push and pop things off of the stack like that. All right. Are there any questions about anything? Okay. All right. I think we're just going to finish today. We will start talking about profiling tomorrow. I really wanted to make sure that I showed you my sample solution for the assignment so that if you feel like you might have missed the mark on testing, or if you feel like you missed the mark on implementing a stack, you can see the way that I've approached it so that you can use that general approach for the third assignment stuff that you're submitting. What you should be able to do today is you should be able to describe the benefits of modularity and use simple metrics to specify the degree of independence, such as coupling and cohesion. So you should be able to use these two words in complete sentences to be able to describe, at least in this state, some abstract concept. So we got a picture. You should be able to say that this is high or tight coupling, low or loose coupling, and high or low cohesion. The second learning outcome we did not get to today, so we will start taking a look at that tomorrow. I otherwise hope that you have a great rest of your day, and I will see you tomorrow.